Okay. So let me start with a sort of, it's not a real theorem, maybe a pseudo theorem, which is just to keep our eyes on the ball. I should say that everything I'll talk about today sort of works over the years with various collaborators, mainly Joel Commentators and Tony Licata, but other people like other related work also involved, related to what I'm going to talk about, like with Josh Shasson and Aaron Lauda and so on. But most of the things I'll go over today are things which have mostly been known by experts for a while. The main piece of which I want to focus on is sort of the vertex operator aspect of things, which again is based on some older work, but I think it hasn't quite been explored as much as I was hoping to do. So anyway, the main result I want to use as sort of an aim towards is the following. So we're going to consider this zigzag algebra, which I'm not altogether familiar with the history completely, but I think it goes back to Covenant and Horofano quite a long time ago. So this is an algebra. We'll consider it of type infinity, but this is just for convenience, just to simplify the notation as we go on. So you can definitely consider finite type, and everything goes through. So the zigzag algebra is the following algebra, which you probably know, but I'll go through it for you. It has infinitely many vertices, which is why it's called type infinity, like so, and it keeps going in all directions. And these are the vertices, 0, 1, 2, and so on. And it's called this graph gamma infinity. And what are the relations? So the algebra is the path algebra of this guy, and the relations, which are the standard relations, are that if you compose basically the length of any length 3 path is 0, and or greater if the 3 path is 0, and any length 2 path, which is not a loop, is also 0. So basically this is 0, everything length 3 is 0. And then finally, if you do have a loop, that's not necessarily 0, or else it's really silly. And you get the final relation is that if you have one loop is equal to any other loop as long as you're fixed vertex. So I should write that as all cycles, all length 2 cycles at the same vertex, starting and ending in the same vertex. At the same vertex. So let me stop there, since I'm sure most of you are familiar with this, and seen it before. And we're going to let an be the symmetry of an times with Sn. So the statement of this pseudo theorem is that one can categorify all the Rashatigan Turek type A Link by assigning in the usual way that what you usually do. For example, in a classical story, you take your length or knot, whatever, and you slice it, and you need to somehow know what to do with each cup and each crossing. So basically, by assigning, I want to say explicit or bimodules. So an modules for the cups. Okay, so that's the main idea. Somehow to explain this result, and it's not really a theorem, of course, because I haven't told you what I mean by explicit, and I haven't told you how to do this. But that's the motivation to explain where these modules come from, and well, in the process, explain maybe the crux of this talk, which is this little story of vertex operators. All right, so this result follows from three relatively, I guess, independent ingredients. Two of which are probably, a lot of you are probably familiar with, one of which is maybe less familiar. So the three ingredients are the following, and you make sure I get them in the right order. The first one is a Heisenberg action, more specifically a categorical Heisenberg action on the direct sum of module categories over these guys. So I'm going to write and by the way, you'll probably notice very quickly that my talk is a little informal, and that's for various reasons, mostly because my purpose of this talk, since it involves various different ideas of which I can't really go into too much detail in 50 minutes, I want to just get a big picture. So I'm going to cut corners here and there and not worry about little details like well, we'll see. But just keep that in mind. So there's probably some commas and things that need to be added here to make this thing completely 100% correct. But I think it's everything I'll say is 99.9% true. So the first thing is this: a categorical action on the category of modules over these guys. The second one is, in some sense, my main point is a categorical vertex operator construction. And as I said, I'm not sure I'll spend that much more time on this point than the other ones, but in some sense, this is the main focus of my main point, at least today. And the last one is maybe something you're most familiar with, which is that categorified or sticking to invariants of type A, to say, can be recovered. So let me see how can I word this. Can be recovered SL infinity actions. Categorical SL infinity actions. Categorical. So in other words, if I knew, I'm being vague again, but I'll be more specific in a moment. But roughly, if I have the right categorization of an appropriate representation of S on infinity, then I can recover some corresponding type A Vertex invariant. And again, if this S on infinity seems a bit odd, just think S on n for n big enough. That's what's really happening. Given our finiteness, and if every given knot is finite, there will always be a fixed n for which I can just do the whole story for SL n where n is big enough. So that's not really an issue. It's just a notational convenience. Okay. Let me see any complaints. If I can still hear me. Okay, so we'll just go through these 3 points. Number one is the content of number one is the following thing. So again, I will just sketch what the contents of these guys are and how they're linked together. That's the goal today. So this result goes back to as a result of Tony Ricotta, which goes back to around, I guess, 2010. Just before us, Michael Kavanagh, he had this paper on categorical Heisenberg actions, and that inspired us, and we wrote right afterwards a more geometrically oriented version of basically his paper. And the result from that paper from 2010, it's basically even though it's not really literally as in terms of A modules, but it's really equivalent to this. So the statement, the claim is that there exists induction and restriction operators that go between AM mod and AM plus 1 mod, and I'll call them PI and QI, where the I is a vertex in gamma I. So the I is a gamma infinity. So for each vertex you have for each vertex I you have 2 operators like this. I guess infinite many operators, because for each n you have an operator that keeps going that way. And for each I you have infinite many operators that go that way, and infinite many operators QI that go this way. And what are the relations such that let's see. The main relation is the one you would recognize most commonly for the Heisenberg, which is somehow that the commutator of PI and QI should be something nice. And so what it is here is that the commutator of PI and QI, which is this, and the isomorphic up to is equal to the commutator is equal to some number of copies of identity. In this case, there's 2 copies. So I'm going to write it like that. Let me not use this notation in case you haven't seen it. Let me just point out that this algebra I just erased. Of course, it's graded because you can grade everything by the length of the paths. So there's everything here. I should write Gmod, but since I'm lazy and I haven't done it so far, I'm not going to write it. But everything is graded in the story. So I'm going to include the gradings because it's so simple to include them, and I think in some context it might actually help you. But if it doesn't, then just ignore them. So here you get 2 copies of the identity, and they're not in the same degree. They're shifted by 1 or -1. Okay, that's not so important, but this way at least I have an exact relation with the board. And there's a similar relation if I is not equal to j. So here you're going to get that this is equal to 1 copy of the identity if I and j are connected, and just no extra copies of the identity. In other words, if j is plus or minus I plus 1, then you get the commutator is 1 copy of the identity. Otherwise, PI and QI commute. Okay. 1 second. Okay, and so that's the commutators. And then the other thing is, I guess a minor thing we can add in here is that PI and QI are bi-adjoint. So adjoint of the right and left adjoints of PI are both QI up to a shift. Shift, and I can tell you what it is, but there's not really any point. Up to a shift of plus or minus 1. And then lastly, this is maybe the most important detail for continuing this talk is that there's an action of some symmetry groups. Maybe I can squeeze it in here. Let me write it like this. There's an action in the symmetry group on the composition of m pi's. If you compose pi n times, you're going to get an action of symmetry group. And likewise, qis. Everything is obviously the bad joint, so there's an action of this guy, is an action. Okay. And there's a couple of that's mostly it. There's a couple of other relations. Well, at least natural transformations, like so S and exponential transformations of these functions. There are a couple of other relations here, but and they're not complicated at all. It would take literally maybe another four lines, but they don't really play a role in the big picture. And so there's no point, I think, mentioning them here. You can always look them up in that paper. So one remark about this is that the nice thing about having this action is that so SM acting on this action, so number 3, so point 3. That there exists, if you have a symmetric group acting or something like that, then you can take the idempotents inside a symmetric group and use them to give you to break this composition into pieces. At least if you're working with vector 60, which of course I am. So that gives you for each partition, it gives you a bunch of I don't want to say new functors, because in some sense they're already there in this composition, but you can pick out a bunch of functors for any partition. And with for the idempotent in symmetric group. Partition of M. So you get a slew of from these operators in this action, you get a slew of sort of newish operators, pi lambda, which and we won't care very much about them, except that psi, at least for the superficial aspects of this talk, we only care about, of course, in general, we care about all of them, but we only care in this talk about pi m, so the one corresponding to the, I guess, one piece partition, and pi 1 to the m, the transpose of it, the one corresponding to as many pieces as possible. So we just care about pi m and pi 1 to the m. Just a reminder. Maybe care is a strong word, but we only see these two guys. Okay. I think that's it. So that's the first point we just erased. It's the existence of this Heisenberg action, together with these natural transformations, of which I only told you one, because that's the main one that we actually that's kind of important to see. And in particular, these natural transformations here give us a bunch more complicated functors, which, if you were to try to write them down explicitly, would be a little bit harder. Whereas this action here is actually very simple. So it's a very conceptual construction. Okay, any questions? So I'm doing on time since I started late. All right. So number 2. Just this Willis operator thing, and in some sense it's the main content. What's the claim here? So this goes back again. It's work with Dara, and I think it goes back to, I guess, 2012. And this is one of those, this is the thing I want to talk about. Sort of, as I said, is the focus of today's talk in some sense, if anything. And it's still sort of bullish work, but we never published this paper. It's on the archive since I think 2012 or 2013 maybe. And well, I think there's a lesson to be learned there. We kept thinking that we can improve certain aspects of it. In particular, there were certain definitions of categorical actions which back then were not so clear, and I think they're not completely clear even today. And we kept thinking that our definition was not really the ideal one. At least I felt that way. And so anyway, so we just put that paper in the back burner, and we kept going back to it every year or so. And well, here we are in 2022. So I think yeah, I think it's probably I didn't quite do the right thing there, but anyway, that paper, it's despite the fact it was never published, it's correct. It's nothing wrong with it, mathematically speaking. So the contents of this of this result is this vertex operator construction, which that could mean various things, but in this context it means very concretely writing down certain complexes in these P's and Q's, and you have an abstract definition of a categorical Heisenberg action in a sense. And of course, we're thinking about applying it to this particular situation, but it doesn't have to be. It's an abstract definition. And when considered certain complexes of these P's and Q's, and from those complexes give an action of the Lie algebra S on infinity. So more specifically, if you have to write down something very concrete, it's the following. So we consider the following complexes. I'm going to write Ci K for the following thing. Let me see if I can squeeze it. I think I can squeeze it. Ci minus. It's going to be Ci minus and Ci plus, two complexes. So the complex is the following thing. The Ci minus is called minus because it goes up to infinity in that direction, at least in principle. It will eventually stop, but this is in degree 0, so it goes in the negative degrees. So the K here, the I is obviously involves the fact that we're going to involve PIs and QIs. The K means that we start with QI to the 1 to the K. Namely, you have K QIs here. That's what the K is. Okay, and that's the first term. And then the next term is you add one more PI, and then you keep doing this. So anyway, if you thought about a symmetric group and things like that, this sort of complex you've probably seen before. So it's not literally this complex, but things like this complex. And just to be precise, there is a grading shift here, which again, it's not important, but I might as well add it since it's simple. And depending on your background, might be insightful. There's a grading shift like that, -1, -2. So maybe the pattern is not clear here, but you add an 1 every step here. And here you're going to have, maybe the not unclear part, you're going to have PI, PI2, PI3, namely these guys. Okay? And there's a similar complex, which I'll denote Ci plus. And it's basically the adjoint of this guy. Remember, these two guys are adjoint to each other, the P's and the Q's. So these, the PIM and the QIM are also adjoint. So if you take the adjoint of this guy, you're going to get a PI to the 1 to the K. Again, after a shift, that's not important. And then a QI, PI, 1 to the K plus 1, and then PI, 1 to the K plus 2. So this is a 2, and so on. And likewise, there's a shift of 1 here. Oh, I left too much space here. There's a shift of 1 here and a shift of 2 here, and so on. So you have these complexes, a couple of technical points, just in case you're wondering, not that it's important, too important. One is that these complexes are actually finite if you're acting on something, because eventually you're acting by, if you look at these guys, these guys exist for n bigger than 0 or equal to 0. They're empty for n less than 0. So if you apply enough q's, wherever you are, you will eventually end up with 0. So eventually these terms will be equal to 0 if you're acting on anything in particular. So anyway, that's not that crucial, but it helps avoid some concerns about the infinity of these complexes. The other one is, well, maybe you might wonder, why do we start with 1 to the k and not just k? Well, there's actually an evolution of this category, which basically at the level of, these guys send pi lambda to pi lambda transpose, right? This is a standard sort of type of evolution when you think about, for example, symmetric group. So then there's an evolution of this whole category, which interchanges pi lambda with pi lambda transpose. And in doing that, you will exchange this complex with qi to the k. So in some sense, it's irrelevant which one you started with. Of course, you get in principle 2 different results, but they're equivalent to each other. And that evolution is actually quite interesting. Again, one of the many things that we never got around to understanding what kind of consequences it has at the level of these complexes. Anyway, so, oh yeah, what are the differentials here? So the differentials. I'll just do it for one of them. The differential, so in the first case, you have qi 1 to the, say, k plus l, and you have pi to the l here, for example, and then you want to just peel off 1. So what you can do is you can embed this into pi l minus 1 pi. So if you look at the composition of pi with pi l minus 1, it gives you one summand is this one, and then you get some other summands. And that's strictly a fact about the symmetric group. Namely, if you take sim L of the standard representation or something like that, and you tensor, sim L minus 1 of the standard representation, and you tensor with the standard one, you get one copy of sim L plus 1 plus some other copy. So this statement here is very elementary. Likewise on this side. And then we said pi and qi are adjoint to each other, so there's an adjoint map here. And if you kept track of the after shift business, you'll see that you get a shift of 1. So there's a map from this guy to the identity shifted by 1. So that's where the differentials are. They're very simple. They basically only involve two simple properties, namely this biadjointness and this action. Okay, and it's also easy to check that this is differential. I'll leave that up to you. It's again a simple fact. So what are these? What's the point of these complexes? Well, they satisfy a nice relation. Following thing. If you take the commutator of Ci plus and Ci minus, but the right one, so let's say Ci k minus 1. Okay, so if you take this complex and you compose it with that guy, notice that they're adjoint to each other, so that's nice. So you have this, and basically it's adjoint. I think there might be a shift of something, shifts going on. But after a shift, they're adjoint to each other. Then what you get is you don't quite get them in the opposite order, but it's shifted by, you get these two guys. You do get a commutator, but the k's change by 2. This relation. I hope I heard it correctly. So the k minus 1s become k plus 1s, and they shift order, plus a bunch of copies of the identity, and the number of copies of the identity is k. Okay. that's the main theorem basically, and there's some other parts to it, but that's the. Because you can also ask about whether commutators of CI and CJ, and I can tell you, but I don't think there's any point writing them down for two reasons. One is that they look similar, and I don't think I'll tell you much more. They're similar to this one, but secondly, because you can summarize it by saying the following thing, namely that this allows you to define, in fact, a categorical SL. This is UQ, but yeah, I guess I can emphasize the Q. SL infinity action. How? By taking EI to CI minus, oops, not minus one, minus, and FI to CI plus. And of course, notice I omitted the K here, but you just have to be a little careful. The point is you have to keep track of which weight space you're in, and depending on which weight space you're in, you're going to define an EI, and the EI is going to be defined in terms of the weight space and some K. So for example, here there's some weight space, and you define the EI is involving the K minus one, and then of course it's adjoint. This is EI FI, and then on the other end, the FI here is in weight space in some other weight space. Notice that this differed by 2, which is exactly how much the pairing of that weight space with alpha. Alpha, if you're working in SL2, for example, of course, the EI and FI take you between 2 different weight spaces differing by 2. That's basically the reason. And here you have an FI EI in opposite order, and then you have K opposite the identity, and this K is again the weight space. So if your weight space K, and you look at the commutator of EI and FI, then if your weight space lambda such that lambda paired with alpha is K, and you look at the commutator, then you get K opposite the identity, and that's what you see here. And so here I'm omitting what K you have to assign because you have to. It depends on some formula depending on what weight space you're at. And I can tell you the formula, but again, it's just some bookkeeping and it doesn't really add anything. The point is, the reason why this theorem exists is because of this basic commutation relation, and likewise one for EI and FJ, namely, well, what do you expect? Okay, so there's a few more, but they can all be summarized basically by, you can guess them now that I told you this, by keeping in mind that you're supposed to be getting a categorical SL infinity action. And again, this in some sense, this is not only the most important one, but also the most difficult one to prove. So once you get this one out of the way, then the pieces fall into place, as they say. So the remark here is that, just to put this into a little bit of context, rather than just a random computation, is that this categorifies what is it? The Frankel Siegel construction. This is a Vertex construction, if you like. And what is this construction? Well, this construction, more specifically, well, this gives you some context of what this result really is. But this construction is basically it's reconstructing the basic representation of the basic affine representation. Sorry, the basic representation of the affine group SLN tilde, or SL infinity tilde, if you like, and from the Heisenberg containing that SLN hat. So again, this is recovering the basic representation from just the Heisenberg subalgebra sitting inside of SLN hat, which by itself is a remarkable just statement if you think about it. So inside of SLN you have the Cartan, right? And instead of S, and of course from the Cartan you can recover, Jack, but from SLN hat you have the Heisenberg sitting inside, and from the Heisenberg inside of SLN hat you can recover basically a lot. That's basically that's kind of the moral of this result. And particularly you can recover the basic representation. And if you basically take this result and you categorize, just keep it altering sum and so on, and unravel what it says, it's literally this stochastic abstraction. Okay, so that's this story. So finally, number 3, which you're probably most familiar with all these things, but I'll quickly go over it just to make things concise. So this goes back even further to work in the around 2008, 2009, I think, early 2008, with Joel Canvasser and Tony Licata. And the statement is the following. So it's basically the statement I said earlier, but maybe a little bit more precise, even though I'm not going to go into all the details. So to categorify all strategic link invariants, type A, it suffices the SL infinity representation, or SLN for n big enough, I guess. V lambda 0. So remember, in this, you can index in SL infinity. You can index the nodes by the integers, or in SLN, if you like SLN hat. You have a special vertex, namely the affine vertex. So this is the lambda 0 is supposed to correspond to the affine vertex. If you really think about SLN hat here, it should be a hat. You think of SL infinity as basically the limiting of SLN hat. And you take the basic representation, and you take so lambda 0, V lambda 0 will be the basic representation, and then you have this generalization of it, M lambda 0. So I guess I can be more precise here. Type not just type A, but type SLM. So if you look in the categorify type SLM invariants, all you need is to categorify this particular representation of SL infinity, where the M is this one. Okay. So what to say about this? So when I refer to this paper, this is really a paper where we first studied skew hydroality. This is where it all comes from. We wouldn't be able to find literally the statement in the original paper, but this is the origin of it is there. And that's where it all comes from. This was sort of spelled out in some subsequent papers, which elaborated in various directions on that main idea. But that main idea is that skew duality plays an important role in relating the braiding to a categorical SLN action. And so let's very quickly recap more specifically how this works. If you have a categorical SLN, very roughly, by categorical SLN infinity action, the caps and cups will be given by the EIs and FIs. Of course, I need to be more precise than that, but it's a very precise recipe, which you probably know by now, and if you don't, reference. But you have this link diagram, you slice it as usual, and then you see cap. Whenever you see cap or a cup, you associate with some EI or FI, depending on the I tells you, depending on where the cap is, and so on. And of course, the more interesting thing is the braiding is given by these complexes, which are complexes which look a little bit similar to the complexes I wrote earlier in terms of the PIs and QIs. So they look like this.
I think there is no sound.
Okay. So on. So these are complexes that I think they have the name associated with them with Ricard, which go back, I guess, to some work of Ricard from, well, I'll need to ask someone else exactly from when, because I don't know precisely when. And of course, Shrangi Ruki had this famous paper from 2004, I believe, where they studied these complexes in the case of SL2, and they proved the abelian-Brouet conjecture for symmetrically. The Brouet conjecture for symmetric. At least, I guess it's some a version of it. So these complexes here, which look similar to the ones I put on the board earlier, they go back, I guess, to the early 2000s. Interestingly enough, maybe even earlier. I don't know, but certainly to the early 2000s. And if you generalize them, you get these, of course, in the natural way, you get these complexes which you're well familiar with, and you get a Bray group action. These guys give you a Bray group action, and together the caps and the caps, together with these ratings, allow you to construct the Link invariance. And of course, these two statements, the fact that you have this braiding is irrelevant of the representation itself is true. The whole point of this particular representation is to have some sort of bookkeeping, which allows you to recover SLM invariance rather than something else. So everything works out so that this is precisely the right representation. So that so the way it works, just very quickly, you start with the braid or the knot, and there's nothing. So you start with the highest weight of this guy, and then when you see the first cup, you go from the highest weight to some particular other weight by some E or F, and then you continue, and then eventually you do whatever you have to do, and then at the end you come back to the highest weight. So the complex, the composition is something that starts from the highest weights and ends at the highest weight, and the highest weight is supposedly a point. It's a very simple. So it's a category of vector spaces. So what you end up in the end is with a complex of vector spaces, and that's their invariant. And the whole point of the content here is that you can always do that, but it won't give you a non-invariant if it doesn't satisfy some basic relations of what the caps have to do with the cups. And if you take this particular representation, it'll do exactly what you need it to do to recover SLM. And it's basically, again, in terms of content, it's basically bookkeeping. It's that the content, really the main content, is that these guys braid and satisfy some natural relation with respect to the EIs. Okay, so that's the and there's a differential here which is extremely similar to the differential I mentioned earlier. So some final remarks in no particular order, just things that come to mind. So of course the most obvious one is just to summarize what happened. So if you put all this together, number 1, 2, and 3 together, with these three, which are in some sense completely independent, you get what you get. You get to start with these complexes. You replace each E5 and F5 by these complexes, and you just get these huge complexes. You get pi lambda UI lambdas for the associated two cups. Compressor, and which recover SLM invariance. And so a priori, these complexes, so in some sense, are very explicit because I told you exactly what to assign to these things, but at the same time, they're very complicated because you have two complexes inside of each other. But they actually simplify a lot, and you can really write down fairly explicitly they're more complicated than the complexes are written down here, like this one and the earlier one, and this one. But you can still write it down explicitly what they are. And again, that's something that we worked out, and we're too sloppy to actually complete it. So it's not actually posted anywhere. So that's the in some sense the point. My motivation for mentioning all of this is because I think there's a lot that hasn't been explored in this situation. In other words, the first one is an obvious question: sort of what moral is there? Recovering all type A invariants.
Sorry, may I ask a question?
In this algebra, start at the beginning, A, which is confusing. From the algebra A that we started from the beginning, this is the zigzag algebra.
I can wait.
From zigzag. A. Of course, I mean, for me, it just seems curious that an algebra which is fairly simple, in some sense, contains everything that you need in terms of ingredients, in terms of the building ingredients to build all your invariants of type A from it. In other words, you can literally write all the, literally write every single functor that you need in terms of very explicit complexes of okay, not literally this algebra A, but at least semi-direct product of this algebra with Sn. What else? So these are again comments in no particular order, except in the first one. Another strange, couple of minutes. Another strange fact is that these operators, which I mentioned earlier, which I would call vertex operators, Ci plus and minus, they make sense very generally if you start with any, in fact, homogeneous algebra. In place of A. One of the things that's special about A is that it's a Frobenius algebra. And the claim is that if you start with any Frobenius algebra, you can repeat the construction I just mentioned. Of course, the difference is that when you look at the commutator, so you can define everything I said, including an analog of the categorical action I mentioned, and an analog of the vertex operators I mentioned, Ci plus and Ci minus. It makes sense. The definitions are completely natural and are not dependent in any way. The differentials I mentioned in Ci plus and minus are not dependent in any way on the algebra A that I started with. So you can define these complexes completely naturally, completely generally, and of course they will satisfy some weird set of relations, and they're not going to satisfy the simple commutation relation I meant, the relatively simple commutation relation I mentioned earlier. But it's interesting I find it interesting that they make sense in this complete generality, meaning that these complexes are in some sense universal, very, very general. And you can do something weird. You can write down a complex for any Frobenius algebra. You can write down basically a complex, or you can get a vector space associated, a complex of vector spaces associated to it, and any link. And of course, that complex of vector spaces will just be garbage in general. I don't really satisfy any properties. But if you start with this particular algebra and you do that construction, then you'll get S-line invariants. It's a very strange thing to maybe think about. And there's various other questions. For example, what is your relation to geometry? I wrote this in terms of the zigzag algebra, but of course, very roughly, if you look at the derived category of A and mod, this is basically more or less, if you're careful, the derived category of coherent sheaves. If you take C2 and you modify by C star, acting anti-diagonally like T inverse, and you look at sort of the Hilbert scheme of this guy. Hilbert scheme. Okay, this might make it uneasy because of the infinity thing, but if I take A to be a finite guy instead of an infinite guy, then I can replace this by C2 mod gamma, where gamma is a finite group. And this is the stack, and this is the Hilbert scheme of that stack. So it's something much more simple. Or if you want, you can take the resolution of that quotient, and that's a genuine, it's an ALE space, it's a genuine thing, and the Hilbert scheme of that guy. So anyway, I wrote this in terms of this to emphasize, in terms of ants, because it's simple to say and to emphasize the simplicity of it all. But of course, you can translate things into Hilbert schemes on these spaces, and then ask. Of course, it's a very good question, but explore what happens when you study everything on the side. And of course, there's people in this conference which study a lot of things on the side and know a lot more than me about this topic. And there's various other things. For example, relation. So some sort of a categorical version of conformal field theory, which I'm less about. Because these Vertex operators, of course, are closely related to conformal field theory, so having a categorical version of it. And this is obviously the most vague question I can possibly pose, but it makes you wonder of trying to understand some various construction of conformal field theory more categorically and some more categorical context. Okay, let me stop there because I've gone over time already.
Very much.
Any questions?
Questions?
So I have a question.
Anything?
Can you hear?
Can you hear us?
Currently, no.
I think he doesn't know that we are speaking because we have.
Yes, we do. Yes, so I'll check. Maybe we need to
put
on the chat. So probably, yeah. So.
We cannot hear you. Yes, you.
Are you still there? I just realized that my thing was not quite on. No, I can't. Yeah, I can't hear you right now. Let me just take this off. Okay, I think this will work now. I can hear you. Okay.
Okay.
Did you hear me during your talk?
Yes. But probably not the converse.
Because I just realized that there's so many buttons I have to press, and I didn't press the button on this thing, and so I was wondering whether. Okay, well, I can hear you now.
That was good, but now we have question. No.
Okay, so are you hearing me, Sabin?
Yeah, I can hear you.
Okay, so my question was, so if you're putting this partition lambda on your PI and QIs, does it mean that you can, so is it related to categorification of invariant for various, so I mean like colored link invariants of type A, or are you mean, so what is exactly type A means? All registering to right package with all colorings, or it's only
yeah, I mean all of them. So the way it would work is you would first do type A colored by fundamental weights. By fundamentals, and so for those, for example, if I have something colored by omega k. Braid is colored by omega k, and I'm starting with the cup. Then I would associate to it E. Say this is strand I plus 1. Like that. Then I'll associate to it EI, something like EI to the k, where this is the k here. Okay. So the way you see the if you want the elementary colors, the colors corresponding to the fundamental representations, coloring this guy is by using the appropriate EI and the EI to the k. And then if you want all colors, it's not an ideal construction, but it's this construction of infinite twists, which at some point I studied, and probably there's other ways of expressing it. But if you wanted, for example, an arbitrary representation, lambda, which you can write as some sum of an I omega I, for example. Then you take a bunch of strands labeled by omega 1, omega 1, omega 2, and so on, where there's m1, omega 1s, m2, omega 2s, and so on. And you would put one of these projectors on it. And these projectors are infinite twists of the full twist. So you take a full twist here, and all the strands go over like this once. And you take this limit, and that's one way at least to categorify the projector corresponding to projecting from the tensor product of these fundamentals to V lambda. If you think of this as being V lambda. So that this construction is completely in this world. It has nothing. It's just strictly in terms of categorical SLN actions. Okay, maybe you can make sense of the braiding and everything here of the caps and so on, and of course of the infinite twist in terms of something living in categorified SLN. The lambdas you see earlier are kind of unrelated. Namely, I told you what to assign to EI. It involved this complex that had like only PM and P1M. But if I needed to tell you what to assign to EI to the K, where K is bigger than 1, then I would have to the complex would actually be more complicated, and I would have to involve more complicated partitions here. So that's all there is. That's where these more complicated lambdas show up. It's just that it's part of the basic story for the Heisenberg. It's not directly related to the knot homology and this lambda and the knot homology.
Okay.
Thanks.
Sergey, you have a question? Sergey raised hand.
Yeah, thank you, Seven, for a very inspiring talk. I actually have several questions, so I hope it's okay. If not, then maybe Chair can cut me off at some point. So first, following up on Anna's question, and also just trying to make sure I understand the big picture, the categorical vertex algebra action is not directly on anything related to topology, for example. It's not acting on cohomology or homology of trefoil knot or anything like that. It's on the ingredients which are used in the construction, right? So it's on this category of AN modules. Yes,
yeah,
exactly.
Yeah, exactly. So you'll get complexes that act between some AN mod and some other. You'll get complexes of bimodules because the PIs are bimodules. So you get complexes of bimodules between of AN, AM bimodules.
So we should not expect that it descends to anything knotty.
I don't know enough to say that whether you shouldn't expect it, but I don't know a direct from what it sounds to it, you have something in mind which I'm not super familiar with some sort of action directly on the knots. And no, I don't see a direct. I'm not even sure what you mean by an action on the knots, but that's all I see at the moment. It's just it's just the relation between the functors basically. The Ci plus and the Ci minus satisfy this relation. That's it.
Yeah. So maybe more specifically, I think it's not going to commute with some constructions like Reidemeister moves or things that we use in building actual knot homology, taking differentials in constructing homological invariants. So
no, but if you take these CIs, which gives you EI and FI, and if you put them together in this way to get bigger things, then those things will
so it will act on huge infinite knots of braids, basically. Yeah. Another question then, more on algebraic side. So it seems to me you landed on a fine Kac-Moody side of this vertex algebra quantum group type correspondence. So in particular for vertex algebra, if it was really VOA, one basic ingredient would be conformal vector. So question is, can you see conformal vector naturally arising in this way?
Yeah, so you mean like things like EI tensor T to the M kind of thing?
Yeah.
Yeah, so I omitted that because it was not so necessary here, but yeah, you do. If you, and in fact, you don't have to change anything. If you want EI, so for example, if EI was given by this complex, so say you're assigned to EI CI, I forget which one it is, it doesn't matter. I'm not going to look it up. Say assign this, then what you would assign to EIM, or EI insert T to the M, you would assign CI minus K plus M. And that's all there is to it.
So what is the central charge of this vertex algebra?
Not sure. Oh, the central charge in this particular, yeah. So if you want, you mean like
yeah, basically conformal vector with itself, fusing conformal vector with itself.
so
I think the Heisenberg had central charge 1, right? The one you said.
fun, yeah. I think
But then
so in particular, you get the basic, the most natural construction, the cleanest one. You get the basic representation of SLN hat. So that's charge 1, I guess. Yeah.
Yeah, so I mean, I know the number, but the question is, do you see it naturally in your construction? That's I'm trying to see how many ingredients of really vertex algebra rather than a Frankfurt smoothie arise.
Yeah, you see it fairly naturally. I don't remember a relation off the top of my head. How do you see the charge again? I forget now. It's like I think
Yeah,
it's
you take conformal vector, fuse it with itself. So yeah.
Well, that I'm not sure I can make sense of right now. Conformal vector. But yeah, you see the charge fairly naturally.
Mm-hmm.
You see that one fairly naturally. How can I explain it? I think if I wrote down maybe all the relations rather than just the ones that don't involve the T and just one of the relations, maybe that would answer your question. And that's a simple thing to start with.
Mm-hmm.
Just give you a screenshot of all the relations, and that might answer your question.
Well, in terms of relations that you wrote, I mean, this vertex operators for really VOA, there would be, for example, quadratic in C pluses and C minuses that you wrote, right? So that's the usual Sugawara type construction. So in that sense, it would require additional steps, which I'm not sure would be motivated or natural.
So let me say it like this. I think to maybe this is the kind of answer you're looking for. I don't know, but if you look at the commutator of CI K with CI minus K, right?
Yeah.
We got 100 copies of the identity, basically, right? But if you put instead of CIK something like CIK plus 1 here, then you're gonna get something like maybe a bunch of copies. I don't remember, but at least something like the P, right? The PI. And if you do it in the opposite order, you're gonna get a QI. And if you take the commutator of these two guys, you're gonna get 1 copy of the identity. And I think the fact, or it's 2 copies. And I think that the content about the charge is somehow captured.
Yeah. That's exactly it. Yes. Thank you. Okay, that's helpful.
Yeah.
I'm getting message.
If I wrote all the relations down, one of the relations would have been the commutator of this thing is something like PI, and the commutator of those ones something like QI.
Yeah, that's exactly what I'm looking for. Good.
Okay.
I'm getting a message that I'll be cut off in a minute, but maybe I can sneak in one more question. So the nature of the talk definitely indicated that it's something about Homfly, right? So do you agree or disagree with that? And if so, what's the connection to elliptic hole algebras and other algebras we see in the Homfly world?
I think it was a bit of a. I don't agree with something about Homfly. I think it's really the algebra A should really be it should really be the corresponding algebra of type affine type M for M really huge. So it's a bit of a red herring. I just put A there to make it cleaner. If you do the non-invariant stuff, the way I know how to do it is to do it is a composition of these three constructions. Then you can ask them independently, how can you get the Homfley stuff? And the Homfley stuff is, so I guess you can try and get, so the thing about the Homfley stuff, right? What's the difference between Homfley and type A? They both involve a Bray group action, which is the same. You can get it from categorical actions in both cases, in fact. The difference between Homfley is that you need some sort of trace. That's basically the main thing. You don't have cups and caps. So here we have cups and caps. If you wanted to somehow reconstruct Homfley from it, and I guess you could probably, I never thought about it, it's a good question. From the Vertex operator stuff, you need a trace, just like you always do. Some sort of trace, which you have to think about where it comes from. I haven't actually. But yeah, it's a good question. I guess that's another direction you can take this, is to ask yourselves how much can you get from the story, how much can you relate it to Homfley, and the answer there is basically you need to make sense of where the trace is coming from. And once you have that, if someone gave it to you, then I think you'll be clearer what. I mean, you have to make a choice about your trace, where the trace comes from. Right? You have some choices. I haven't explored that side of things.
Yeah, thank you so much. I won't take more of your time, but want to thank you for all the answers and wonderful, inspiring talk.
Thank you. But the A in the beginning is a red herring, I should say. It's, that's not really, you shouldn't think, oh, A infinity, so it should be a Homfley. There probably is a connection with Homfley, but not just that.
So maybe you could continue the discussion afterwards, but this time we'll speak again.